All right, thank you everyone for showing up for my presentation today. I'll be talking on breakthroughs in semantic analysis, more introducing the concept of static analysis, talk a bit about what it is, why you should be doing it, and how you can do it, and then how you can do it really well. So that's kind of the basic overview here. But before I get going, let me start out by doing a quick introduction just to who I am, so you know who you're getting this information from. To begin with, and before I even talk about that, let me first say that I'm not James Croall. He unfortunately could not make it today. He is one of my good colleagues and friends, but was not able to make it. So I am I'm here kind of in his place. We're planning on speaking together, but since he wasn't able to make it, I am here. So I am David Lindsay. I am historically I would call myself a security researcher, or security consultant, or security engineer. I actually started out getting a degree in mathematics and thought I would go into Java development or C development, but ended up in my first job out of college, I ended up doing a lot of software testing, and that quickly led into security type of testing. And I found out I had kind of a good knack for breaking applications as the security, as we would say in the security world. But I've worked really closely with developers over the last 10 years to do code reviews, to do manual penetration testing, to do architectural analysis, threat modeling on applications, all these different types of security techniques that can help make applications better. And so I really have a strong passion about making applications more secure, and that so security is kind of at the heart of it, but it extends beyond just security as well. In order to make strong, robust applications, taking quality type of issues into account as well is also important. And so so now my role at Coverity, I'm a security product manager, and I really like working at Coverity because our focus is 100% on making developers, empowering developers to write more secure code and more, higher quality code. I don't want to focus too much on the company or the our products, because that's not really the focus of the talk. But I will mention a couple things later on, but I'll keep it to a minimum. So the testing that we do, is important, and we call it development testing. And the reason why is because, organizations oftentimes have separate, quality assurance groups that do their own testing, and that's certainly important and valuable. One of the main reasons why development-focused testing is important is because, for one, the sooner you find defects, the better it is. It's much more costly to rely just on quality assurance groups to find things after the code's been written. For example, it's very normal to in a waterfall or agile scenario for a QA team to find defects a few days or a few weeks or even a few months after the code's been written. And certainly they're needed to find certain defects, but there's a certain subset of those defects that the QA groups find that actually could be found earlier, and it's much cheaper and more beneficial to everyone involved to actually find them sooner. And so that's why we try to really focus and enable developers to do their own testing. One of the reasons. I'll talk about a few more reasons in a second. So just, if you think about all the defects that, skipped ahead here. All the defects that, can possibly, be caught, there's actually a good number that can be addressed at the development stage. And by doing so, there's many benefits that are to be gained from that. So static analysis is one type of testing technique that can be done at the development level when the code is actually being written, and that's really one of the main advantages of doing static analysis testing. It's just that it happens about as early as you can possibly do it, really, and so. But there are other testing techniques that are out there. Another common technique, for example, is called dynamic testing, and you can use both static or dynamic testing to find different types of issues on the quality side and on the security side, and they both are very good at finding different types of defects, and there's even some overlap where certain types of issues you can find very well with both tools. But I like, both analysis techniques. But I like to tell people that really, any organization or any developer should be looking at having, both types of testing occur. But for developers, I like to focus on the static side because that's a little bit more hands-on on something that a developer can take ownership of and do, right there on his or her own desktop. So another important distinction that I'll be talking about a little bit later on is, the difference between analyzing the actual source code versus analyzing binaries. There, are pros and cons to each. I like to focus on the actual source code itself because when you are looking at the raw source, you just get more information. It's easier to report back, specific spots in the code where defects exist, or to show code traces or pass through the code where vulnerabilities exist. And so it's really, a beneficial way, but a beneficial way of doing static analysis. But on the other hand, if you analyze the binary code, that actually, or excuse me, the bytecode, for example, with Java, there's certain advantages there too, because then in that case, you're not as dependent on the actual language that it was written in. So you can have a little bit more applicability to languages besides just Java, for example. So there's definitely pros and cons on both fronts there. So I want to talk a little bit about why people should do a static analysis besides just the cost benefits. But before we get into this, can I just get a raise of hands who, in the audience does some form of static analysis testing, whether it's SonarQube, find bugs, a proprietary tool, like Coverity, or even the security tools like Fortify. So it looks like well over 70 or 80% of the audience looks like they are doing something, which is really good. That's because it's a great starting point for finding these types of issues. So for those of you that didn't raise your hand, I just have a small blurb for you. So why should you start doing it if you're not? Well, there's an example here of Maurice Wilkes, he helped develop one of the first computers, talking about how he quickly came to realize that that a large part of programming isn't just about writing the code and having it run, but it's actually getting it to work in the right way and finding mistakes in your code. The way I like to compare or think about it is, here, like an example, let me give. So my wife, she is an author. She likes to write poems, short stories, and sometimes longer novels, and she is much better at it than I ever will be. I really suck at writing, but I am also somebody that she will turn to review some of her writing before she, as part of her polishing process. And she actually spends a lot of time rewriting and rewriting and writing. So I have lots of good opportunities to give her feedback. And sometimes, she wants really high-level feedback, like, does the plot line, flow from this section to this section well, or can you just tell me about this paragraph? Did I word everything properly? So there's different levels of feedback, but the main value and why I am able to provide feedback isn't because I'm a great writer or because I'm a technical editor or anything like that. It's just because I'm an independent third party, and so there might, for example, be like a sentence that she's written that just has two words swapped or has a word repeated twice, and she will read that same sentence 10 times over and not catch that little error. But when I look at it with fresh eyes, it just pops out at me. It's real easy to see that. And so even though it's not something I'm great at, I can still provide a lot of valuable feedback to her just because I am an independent person and I'm not so embedded into some of the problems that she's trying to solve. So take that whole scenario and translate it to code that's being written. It's the exact same. There's very minute detail-oriented semantics of the code type of issues that you might not just see because you're so ingrained in the problem, or there might be higher level issues with how this section of code interacts with this section of the code. And sometimes it's really beneficial just to have an outside opinion to do that. And fortunately, on the code side, it's really easy to automate. My wife, I don't think is as fortunate. It's not so easy to automate, technical review of some of the writing. But at least with source code, there's actually some really good tools out there, both on commercial tools and open source tools that will automate this process so that you can pretty much have ongoing live feedback of your code as you write it. And if you think about it, that's really valuable, and it'd be silly not to take advantage of some of these tools that are out there. So let's talk a little bit about Java specifically. So Java gets compiled to bytecode, and so you have a couple different options in a language like Java on how you do analysis statically. So direct, first option that I'll talk about is, what I mentioned before, and that's by looking at the bytecode. And that's certainly a useful, valid technique. And like I mentioned before, one of the main benefits of doing that is that, any other, JVM language can also be analyzed, without having to change a lot of the underlying analysis. There's maybe some customization that needs done, but so it has a little bit broader breadth when you do it this way. But on the other hand, it's a little bit more difficult to give feedback on specific parts of the code, and you kind of have to infer certain things, and you don't necessarily have access to config files and so forth. And so providing actionable remediation advice and things like that gets a little bit more tricky. And so in our experience at Coverity, we've done analysis both ways, and we currently can do it both ways. But we found that by focusing on the actual source code analysis, we can provide a much deeper, thorough coverage. Now, in talking about source code analysis, I'm not talking about, writing, using egrep to search through your source code to highlight every instance of, a method that's used. You can write those kind of checkers, and they maybe are useful for following adherence to certain coding standards, but that's a really, really shallow type of checker. When you're analyzing source code, you can actually go much, much deeper than that, and I'll talk about some of those. I'll give a couple of specific examples here in a minute. I wanted to just give a basic overview of how the workflow works if you are doing kind of a deeper analysis. So, like I said, if you're looking at the source code, you don't just want to grep through the code and find these really shallow issues. You want to look deeper, and you can do that by beginning by looking at how the code gets compiled, and by seeing the compilation process, you can extract bits of information from that. And for example, the abstract syntax tree that gets built, the compilers do something similar, but our analysis, for example, pulls that information out and stores it in its own directory, and that kind of provides one of the starting points for doing a deeper analysis. From that, you can also look at building things like a control flow graph that also provides information about which methods call which methods, and that allows you to start, doing more interesting types of queries in the code, or more interesting types of analysis techniques where you can start saying, okay, this part of the code is connected to this part, and you can see that maybe, something that's initialized over here is maybe being used insecurely over here, or a resource that's created here. You can see if through all paths in the code, is it being properly closed. So by doing this kind of control flow graph analysis, you can actually you can find a lot more interesting and deeper types of defects. The other thing I want to talk about is there's kind of the three steps. So the first step that I like to think about is monitoring the build process and extracting out the important parts of the information. Next, you can act on that and do the analysis to find defects on those bits, the core parts of the source code that you've extracted. And the final step then is you need to, present the defects that you find back to the developer. And there's different ways you can do that. If you have an IDE integration, that's a really nice, convenient way, because then it's just right there on the developer's, desktop, and really easy to identify, in the source code, hey, this line of code, you did something wrong. You should, consider doing it this way. So IDE integration is one way. You can also, we have an option, for example, in our tool where you can present that information in a standalone web GUI. But either way, you want to make sure that you are providing, actionable remediation advice. And the other key thing I should mention here too is that, I'll talk about this a bit later, but when you have a tool that is reporting back defects to developers, it's really important that you don't waste their time with bad information. And I say that because there's actually a lot of tools out there that do that will report either, a lot of issues that are maybe real issues, but maybe not ones that care about that much. Maybe they're more like coding style type of rules. Or even worse, there's, a lot of tools out there that just have lots of just flat out false positives that are just completely wrong. It's not unheard of, especially in the security world, this is true. There's tools out there that, for example, have 95, 98% false positive rates. And that might be fine for a security auditor who has the time and know-how to dive in and triage those kind of defects and focus on just the ones that they care about. But for a developer, that would never fly. In our own testing and research, we found that about 20% is the cutoff level for false positives. If you have higher than 20% false positive ratio, then that's the point where developers start tuning out and not using their tool. So that makes it actually even more challenging to do static analysis and do it well. So I'm getting a bit ahead of myself. I'll come back to that in just a minute and talk a little bit more about why false positives are important. But next I want to talk a little bit about just what are some of the types of analysis that can be done on a Java application. So there's a few different categories I've broken up here. The two main ones are intra-procedural and inter-procedural analysis. The main difference here just is being like the scope of what you're looking at. In intra-procedural analysis, you'll maybe look at, within a particular method, look at code paths through, loops and through conditional statements. And you can do certain types of analysis on, just within that method to identify bad patterns. It's kind of similar to that, but kind of stepping up a level is to do the inter-procedural analysis. And we do this, or one way to do this is by, creating a summary of a method and then looking at how the different summaries, interact with each other. And that can also provide different types of information in the feedback. So kind of related to the inter-procedural analysis, you can do things like data flow analysis. And I like to think of this as tracking, data that, external data that comes into your application. And in particular, not all data that gets sent to your application is necessarily trusted. For example, if you've ever written a web application that, has any sort of interaction with users, they probably can submit data to your application. And in a lot of cases, your users aren't necessarily to be trusted. And so you need to do, certain things to make sure you are handling this untrusted data properly. Unfortunately, most, it's the default things in most Java frameworks and other languages is to not handle untrusted data properly. They just will pass through without making any modifications, and that actually, in most cases, is going to lead to security vulnerabilities. The smarter thing to do, obviously, would be to do, for example, some sort of escaping or sanitization on the untrusted data. That way you know that it's being handled properly, but usually you have to explicitly take steps to make sure that kind of sanitization happens. And so that's why data flow is, an important type of analysis, and oftentimes one that developers forget about or leave out, because they don't have the right sort of sanitization in their code. I'm going to refer to this a little bit later too about data flow. So we talk about, when we're looking at data flow, sources and sinks. A source is where you have untrusted data that comes into the application. Sink is where that untrusted data leaves the application. A good example would be like a username maybe that gets submitted as part of a login process, or maybe username and password. So those are both untrusted data that come in, and maybe they get added to a string in some way, and then maybe later on the username and password get added to a SQL query. And if they are not done properly, then a malicious user can add additional SQL constructs to that query that will modify the meaning of the original SQL statement. And so now instead of just having a SQL statement that logs the user or checks to see, for example, if the user has a valid password, now you have a SQL statement that will always evaluate to true or will always allow the user to log in, for example. Or perhaps an attacker could include a nested SQL statement that extracts out other information from the database that they shouldn't even have access to. So that's, for example, one case where you have untrusted data coming in at the source and then being used in the sink. Before I forget, another interesting type of analysis that you can do, and not all tools do this, but it's what we call statistical analysis. So an example might be that maybe you check a certain variable to see if it's null in 19 places in the code, but we notice another instance where that same variable is used but hasn't been checked for null. That's actually really either indicates that you have a lot of unnecessary null checks, or maybe you just forgot to put the null check there on that one case. And that's the sort of a good example of kind of the statistical type of checker where we can look for, where if we identify through statistical means that certain patterns are being followed by the developer, but not in other cases, then we can highlight that. And this actually has been really, I've seen a lot of developers really surprised at the types of things that the statistical checker can find. And I'll show an example of this here in just a second. So, at its core, finding defects is hard, but it's not the only hard part. The other really hard thing about finding defects is, the eliminating false positives, like I said. If you think about it, it'd be really simple to write a trivial, static analysis checker that pretty much flagged everything. Sure, it doesn't have any false, it doesn't have any false it doesn't have any false positives. It flagged everything, so all the actual issues in there were flagged, but it's also going to have so many false negatives in this case that so many false positives in this case that it's completely useless. So the being able to actually distinguish meaningfully between real issues and non-issues is really a hard problem to tackle, and it's one that a lot of tools do maybe a marginal job at, but don't do a great job at. So let's get a little more technical and talk about how some of the analysis actually works. So I don't have time to go into all the details here, but let me just kind of present a simple scenario here. So we have, I talked about how the analysis builds, abstract syntax tree and a control flow graph where we can see how different, parts of the code interact. So I'm showing here on this slide just, in a very, very simplified example of, what that control flow graph might look like. And now in the analysis that we do, we'd want to look at different, paths through the code. And not just the different paths through the code, but also all the different states that you can be at each node in this graph. And the types of questions we want to ask, like, do you ever reach a certain state? These are fundamentally impossible questions to always have answers to. This all comes back to the halting problem, really. But so the key isn't, to try to analyze every single possible path and state that your application can be in, but somehow we need to be smarter and narrow it down to a smaller search space, or narrow it down to parts of the code that are more interesting. And so there's a whole bunch of tricks and techniques that can be employed to do that, and that's really where the guts of doing a smart analysis comes from. So I'll talk about one example of how we can simplify the search space, or to make it easier to navigate through a control flow graph. So this is an even more simplified version. So in this case we have 7 different nodes here, and so the question is, first off, how many different paths are there through the graph here if you're going from A to G? Any hands? Yep, I hear it somewhere. It's 4. So there's 4 different unique paths here. A, B, D, E, G, and so forth. So, or you just think about it, at A there's 2 branches, at D there's 2 branches. Anyways, so one way you can simplify, the types of, the number of checks or the number of paths you have to check through the control flow graph is to do certain kind of intelligent caching. Now, this doesn't always work. There's only certain situations where you can do this, but if certain conditions are met, this can be really powerful. And so let me give a quick example of how that might work. So if we, as part of our analysis, came to this, construct in the code, we maybe would start out going down the ABD branch, so taking the true path in the first decision. And then at D, then we have another choice, and again we'd take the true path, so we'd go D, E, G. So we just explored one of those 4 paths, right? Now we're at G, and we will backtrack back until to the previous decision point. So we'd go back to D, and then we can go the other path, the false path, and go D, F, G. So we've now completed 2 of the paths from A to G, right? Okay, so now we're at G, but we're going to backtrack. We'll go back to D. We've already explored all the paths there, so we'll backtrack again to A. And now we can take the initial false branch that goes A, C, D. And now we're at D, and this is where the caching comes into play, because if we are smart and we are doing the caching properly, then we can recognize that we've seen this situation before. We're sitting at node D, and we've already explored both of these paths and with slightly different history, but looking forward from D, the 2 paths from DEG and DFG, those are both paths we've already explored. And so this is a situation where we could apply the caching and then say, okay, I don't need to explore any further because I've already been down that road, all the possible paths beyond this point. And so by employing caching at that level, can actually save a lot of time and help eliminate a lot of false positives. So that's one example of how our analysis, static analysis through the code can be simplified in order to help eliminate false positives. I want to give one other example of just how we do more intelligent things, and this is going to be more of a data flow analysis, data flow example. So I talked about this a little bit earlier with SQL injection, how you might have an untrusted username and password that gets passed in. That's the tainted data, goes into the source, and goes through the code and passes out of the sink. And kind of at a naive level, you could flag that that construct just by itself, as a vulnerability. But then you'll probably have some false positives or false negatives related to that if you don't take into account, an escaper that happens at step C. So maybe the developer, was anticipating that there'd be untrusted data here, they're doing the right thing, and so they added an escaper in. And that escaper, can detect. So kind of stepping up the quality of the analysis is then you need to be able to recognize these types of escapers. And there's lots of different heuristics you could use to understand escapers. And like at a naive level, you could look at how it's named, or you could look at how it behaves in some ways. So I'm not saying this is the only way, but one way you could do a more intelligent analysis on that escaper to figure out what it really goes on is something like this. So you could do dynamic fuzzing on that escaper. So kind of treat it as an independent code block and look at what gets passed into that method, look what gets passed out. And you wouldn't obviously want to do this for every single method between the source and the sink, but maybe certain ones that match certain patterns. Like maybe if a string gets passed in and a string gets passed out, that might be a good candidate because there's a higher probability than that there's some sort of interesting escaping going on in this routine. So in that case, then maybe we would do like a dynamic fuzzing on that and see, okay, what happens if we send in a string that has a single quote or a double quote or a open bracket, these types of characters, because from an attacker's or security point of view, these are the kind of characters that an attacker would want to inject in order to do something malicious. And so you can do this kind of dynamic fuzzing on the escaper to understand exactly how it behaves, what gets passed in and what's passed out. And so if you have that bit of information about how the escaper actually behaves on certain important characters, and then you can do this other step, which is understand how the tainted data is actually getting used. So, in a lot of cases with data flow analysis type vulnerabilities or security defects in general, in a lot of cases, that string is going to be, concatenated into other strings. And so let's take a cross-site scripting example where the string is ultimately going to end up as part of an HTML response. Well, that, in a lot of cases, the tainted data would be, constructed into an HTML string, and then that string will be put onto the, sent in the HTTP response. But so it's important to know that the tainted data is being added to an HTML page or a string that's part of HTML, but we want to know even more than that. We want to know, is the tainted string being used in between two tags? Is it being used inside JavaScript? Is it being used inside a JavaScript string? Is it being used inside a JavaScript comment? Is it being used in CSS? Is it being used in an element attribute? All of these are different places where the where a untrusted data might end up, but there's different implications for each of these scenarios. And in one scenario, for example, an attacker might only need to inject a semicolon in order to escape out and do something malicious. In other cases, they might need to inject a single quote or a double quote, or if you're in Internet Explorer, backtick quotes. So there's all these different scenarios that you have to take into account. And so by understanding the context of how your tainted string is being used, you can actually be much more smarter about being able to recognize when you're actually in a vulnerable situation. So the way we do that is to recognize that we're in HTML and where in the HTML we are. We use kind of a context-free grammar on the strings, and that provides that information. And then we couple that with what information we have about the escaper and knowing what characters might come through unfiltered there. That allows us to be much more precise about saying if there's actually a vulnerability or not. And so this is the kind of technique that very few static analysis tools actually do, but it's like I said, very, very powerful and useful in terms of making sure you don't report false negatives. Okay, so So, I talked a little bit about some of what's going on under the hood in terms of, the static analysis engine. The next question I want to talk about is, well, what's actually found? What types of defects can you find using static analysis? So I just have a couple slides here that just provide, a kind of a dump of different types of issues. I'll just highlight, I guess, a few of the interesting ones here. So we just talked about cross-site scripting, and that's obviously a very, very prevalent security issue in a lot of web applications. SQL injection is also very severe. There's been a lot of companies that have been on the headline news for bad reasons because of SQL injection type issues. Similar to that is command injection issues. I'll show an example of a command injection issue in just a minute. So there's also like resource leaks types of issues. Those obviously can have a lot of bad consequences for an application, causing it to crash or to behave unreliably. Certainly like null pointer dereferences, logic errors. Moving on to the next slide. So control flow issues, those are more like some of the intra-procedural analysis type issues that I mentioned earlier. And then, we can also, you can also identify some higher level or more shallow issues of, things related to code maintainability or coding standards or coding styles. So one thing that, it's important to highlight is that, the 80-20 rule certainly applies with static analysis in that, maybe 80% of the defects that are present in an application are found with just 20% of the checkers. That's turns out to be quite common in a lot of applications. But that doesn't mean that the other checkers aren't valuable. I think command injection is a really good example of that, where it's a very if a malicious user or an attacker is able to somehow inject Java code or inject into your command line code. That can have very, significant impact, have very serious security consequences, not just for the application, but for, a whole company. And if, millions of credit cards are leaked through something like this, that's obviously really bad. And, those types of situations have happened. But the point I'm trying to make though is that command injection is not something that's very common. But when it does, when it is present in a code, it's definitely something you want to know about, and it's something you want to be made aware of. So the takeaway is just because a defect isn't very common or doesn't fire a lot doesn't mean it's not important. It's oftentimes quite the opposite, that those are the ones you want to spend the most time on or spend the most attention on. So let me kind of talk at the code level a little bit about some of the types of defects that we can find. So one good example is just kind of a check for null references. So like you might have, for example, in a code where you check a particular variable x to see if it's not null, and then later on you use x without being checked. Obviously, that's something we know to flag. But in the reverse order, it's something we could flag too, where maybe you first use x and it's not being checked for null, but later on you do. In both cases, we can say, there's inconsistent behavior here, and so maybe this is a situation where you'd want to flag, where x should always be checked for null, or perhaps you have unnecessary checks for null. So resource leaks. So I was actually just talking with one of my colleagues, about an hour ago before this presentation talked, and he had this really great story actually about how resource leaks can be really devastating. So he had gone on site, was talking with some developers on a Java application, and this was this government organization somewhere here in Europe. I forget which country, but they. We're doing an evaluation on one of their applications, and they had this unfortunate problem that the application was crashing consistently over and over and over. And so we kind of were asking, well, what's going on? And they said, oh, well, it just does that. It's done that for 4 years now, ever since the application was first written, and we just live with it now. And it's just part of their day-to-day workflow that they would be restarting this application multiple times a day. And so we're like, okay, yeah, that's weird. But so we did our analysis, and as part of the analysis that we did, we found several resource leak vulnerabilities, and 4 of them the developer was able to zone in on really quickly and say, that's suspicious, let me hurry and fix those. And they fixed them overnight. The next day we reran the analysis and they were gone, and they also redeployed the application and the crashing stopped. I mean, that was it. They had these 4 simple resource leaks that were in the code, but through their own manual code reviews and whatnot, they weren't able to find them. But employing a static analysis tool, they just popped up like that, and they were able to easily pick out that and have this this huge problem just go away overnight. So. I like to I just think that's a really good example of how on the one hand easy it can be to fix some of these things, but on the other hand how hard it can be too, because they went for 4 years without really doing anything. So threading is another type of issue where it's easy to get into trouble. So for example, you might access a particular object with a lock object 19 times out of 20, but that one time out of 20 where you didn't, that's a pattern we can recognize and say, hey, you didn't access this in the same way, and we can flag that as a potential threading issue that can also cause code stability issues. So I mentioned the statistical checkers earlier. This is an example of how like a copy-paste error can be present in an application. These are the ones that I think are really nice because it gets people's attention. So if you look at the 2 different methods here, code snippets here, the second one is a cut and paste of the top one, and you can tell that there's a few variables that have been changed, right? So spend just a second looking at that. I can see real easy from the first line that the variable locals was replaced the variable returns, and so you'd imagine that probably they meant to do that all throughout the copied code snippet, right? But can you see where they missed something? I mean, it doesn't stand out right away. So let me highlight it. Yeah. So right there on the last line, you can see that it has the original returns value from the first method, and they probably meant to replace it with the locals from the second, from this, as part of the replacement. But that's a manual thing that the developer had to do to replace that one variable, and they just missed it in one spot. This is actually really common. When I say really common, I guess it's all relative, but it's not unusual for us to find at least a few instances of this in any given application that we look at, and it's really nice to show people that this kind of these kind of findings too, because it's just like, oh yeah, that's really simple and obvious. But so are there things that can be done better statically? Certainly, there's always improvements to be made, in terms of the types of languages that are being covered, the types of, how you handle, which actual true positives you're able to detect, how you eliminate false positives. And I know, for example, here at Coverity, we're constantly making improvements in all these fronts so that we can do more in-depth analysis. So there's definitely, a wide, a lot of growth to be done in this space, but I'll talk about CodeSpotter in just a second. But first, I know that I asked people to raise their hands earlier about who uses tools, and I know from previous experience that most people here are using a tool like SonarQube or Find Bugs, and that's great because to be honest, they're free and easy to download. They're easy to work with, and so it makes sense that that's where a lot of people start out using in terms of using a static analysis tool. I put this slide together just to kind of highlight, what you might be missing if that's all you're doing. And so, I talked a bit about inter and intra-procedural analysis. A tool like Find Bugs, it does, intra-procedural analysis as well. It's able to do some data flow. It's able to, to do some some navigation of the, paths through the control flow graph. But, it's kind of limited to some of those areas, things like the dynamic testing that can be done, or some of the inter-procedural data flow type, or the statistical type of analysis. All of that are things that you might be missing if you're using a tool like Find Bugs. So again, I don't want to be dissing on it. I mean, it's a great starting point, but if that's all you're doing, you should maybe look at upgrading some point in the future to something that goes a lot deeper. So continuing it just for one more slide, that comparison. So the actual defects that can be found. There is some overlap between like what a tool like FindBugs would find or what a deeper analysis tool like Coverity could find, but it's actually pretty shallow, and it's because at least at Coverity we focus on just different types of issues for the most part, and we even include FindBugs integrated into our analysis so that if you want to see those issues, we can easily flip a switch and turn those on, and you can see those as well. But really, the value you're going to get out of a deeper analysis tool will be in the highlighted section there. But again, I'm not trying to plug our tools, so I'm going to skip over those real quick. So let me show some of the types of actual real-world issues that can be found. And you'll have to forgive me because the first one I wanted to show made the news recently, but it's not a job application. So, but I figured it's worth highlighting just because the same kind of pattern could happen just as easily in a job application. So this is the Apple go-to fail. Has anybody heard of this? Yeah, good number? Okay, so I'll describe just real briefly what happens. So as part of Apple's certificate checking methods for SSL certificates, they needed to, well, there's a lot of code into how to properly check the certificates, and I don't want to get into the details there because I don't think anybody understands how to do that properly. But in part of the logic they had for checking certificates and making sure they were proper, they had kind of a switch statement like this, or several if statements, and probably either through a copy-paste error or through some sort of just probably trivial coding error that was accidental, or I guess if you're a conspiracy theorist, maybe you think it would be intentional. But either way, this extra go-to fail line showed in on line 92, and so it's really easy to see if you're looking at it that that shouldn't be there. That's, but it's the sort of thing that was not initially detected when the code was written, and I don't know if Apple had internal code reviews or whatnot, but it went for several years without being detected. And so just the fact that that simple, extra go-to fail line was present in the code meant that, there's a certain section of code after this that got skipped. And that's the sort of thing that can easily be identified using static analysis, because there's a big chunk of dead code, and we can raise that as an issue and say, hey, something fishy is going on here. You have a whole section of code here that's not ever getting executed properly. What's going on? So even though that wasn't necessarily a security-specific type of checker we have, it's still, because this was in security-sensitive code, it still, kind of led to a very serious security vulnerability. Okay, so one other example on my slide, and then I'll switch over to my browser so you can see kind of more hands-on. So I talked a little bit about how you can, look for null pointer exceptions, or where you maybe have cases where you check for nulls in certain cases, but maybe you miss all the cases. So this is an example where that's possible. But I like this example because it's not immediately obvious what's going on. And I apologize if the screen's kind of hard to read, but I'll help fill in some of the details. On the first line that's being highlighted, line 115, there's a check for the variable g not being null, and if so, it does something. Later on, there's some other code, but it doesn't directly reference the variable g at this point. But there's still a use of g without checking for null that happens, and you don't see it, but let me highlight what's going on. So in the highlight in red, we talk about the get state string variable, which is kind of at the end of line 116. And if you go into that method and see what's going on, so I kind of highlighted the get string, or excuse me, get state string method. But if you drill into that method and see what actually is going on, the variable g actually is being used here. And even knowing that, if you look at the code here, it doesn't immediately stand out. So I highlighted it right there. So there's the same variable g now getting used without that null check. So this is a good example, where it's happening interprocedurally. It's not just in the same method, but in a completely different part of the code now. This variable is not getting checked for null. So that's the sort of thing that could potentially have very bad consequences for the application, causing it to crash in some scenarios. Okay, so let me switch to my browser. I've got just a few minutes left here. Here we go. Can I make that bigger? Yeah, there we go. Okay, so I wanted to show just how some of these real vulnerabilities might be reported back in a tool, so that you can see. So in this case, I wanted to highlight a simple SQL injection vulnerability. And the tool here that we use for displaying vulnerabilities, we try to have it be very developer friendly. And that's why you can see the source code. You can navigate through the source code, kind of very similar to an IDE. But we also have IDE plugins if you prefer to work directly in your IDE to do the same kind of work. But the important thing is that when you're looking at a defect for the first time, you need to be able to quickly triage and decide, is this a real issue or not? Or decide at least what kind of actions do I need to take? Is this something I'm going to fix right away? Is it something I'm going to hand over to my friend who actually wrote that code? So for the SQL injection vulnerability, we try to make that really easy to trace through the code. So to start out with, we have where data is getting read into the application here through the request param, and then it gets passed through the kind of the different hops through the code are down here in the corner. I'll kind of spare you the details and just jump right to the sink. And so, let me go back real quick. So the variable in question here is the variable the string hint. So I just highlight it there so you can see how it's being used. But let me jump through the code here, and it happens to have the same name here at the sink, and you can see the same variable now is being added to the SQL statement. It's actually a nested select statement. But in doing the analysis from that source to sink, we've identified that there's no escaping going on. And so this is a very classic example of how a SQL injection can be present in an application. Let me switch to another example here. There we go. So let's do a cross-site scripting example. So this is one that's all self-contained in a single method. So this is kind of a classic example of what I'd call a reflected cross-site scripting. So the beginning here is, that's the end. So the beginning here, line 1. So you have just a very standard request.get parameter answer, and that's being stored as the variable answer. So I've highlighted that variable so you can kind of see where it's being used in the code here. So again, I apologize if that's hard to read, but this is the variable answer, and then immediately after that, you can see the code here that's that's constructing parts of the HTML page that are going to be included in the response. They're adding in paragraph tags and input tag, and then as part of that input tag, you can see the variable answer getting directly added now to that HTML page. And there was no sanitization between the two. This is a very, very easy, trivial to spot type of cross-site scripting error. Let me do another one here. Let's see, I got a few more minutes. So we talked. I already gave a few examples of where there's improper null checking. This is another example where that happens. I'll skip this one. Let's see. So I mentioned earlier the code injection one. So in the struts framework, is that one that people commonly use? Anyone use struts? Okay, at least a few people do. So, in our experience, it's one of the more popular frameworks that are used by Java programmers, and it has its own OGNL kind of query language that's built into the struts framework. And if you're able to, like, if a remote person or a remote attacker is able to execute OGNL, it's kind of the same as being able to execute Java, or I was going to say JavaScript. It's like being able to execute Java code itself. So you want to be careful that any untrusted data does not get used in a situation where OGNL constructs will be dynamically evaluated. And so by understanding, first off, you have to have solid understanding how the struts framework works and that it's using OGNL, and then you have to understand where these sinks are, where data might end up, where it will end up getting evaluated, or where any OGNL constructs will get dynamically evaluated. And so if you're able to do all that, and then also check for the proper escapers or sanitizers between the sources and sinks, then you might end up with this kind of an issue. So in this case, you have data coming in through the get page title. And then the sink here, go down 5. Oh yes, it's just right here where it returns the get text. This happens to be a situation which we know, through our understanding of how struts works, that that any variable that gets passed to this method will be, any OGNL constructs in that string will be dynamically evaluated. So this is a very definite case where OGNL injection is possible, assuming that, an attacker can originally, submit, the injected data to begin with, which in this case they could. So, again, it's a very, high severity issue, but one that, if you're just doing your manual code review or you're just looking, if this is code you just had written, it's easy to overlook these types of things. It's not the sort of, defect that just pops out at you. So just in the last minute here that I have, I just want to talk about how, let me go back to my slides. So a couple different ways if you're interested in doing kind of deeper analysis in your code. There's obviously a lot of tools that you can use, but I'd like to at least suggest a couple ways that you can use Coverity to analyze your code. One is through our online Coverity as a service offering, where you can upload your application or some application you want to do evaluation on, and you can have that done. You can kind of do the build step locally on your machine and upload the artifacts to the cloud, and then we'll run our analysis on the cloud. That way you don't. That way, we can do our really in-depth analysis and not, tie up, even if you don't have enough memory on your machine, for example. But at the end of the day, you're able to get feedback in terms of, on exactly these types of issues. And if you want to have, find bug checkers included in that, we can do that as well. But like I said, really the value will be on these extra, deeper types of checks that you can do, like with the data flow or the statistical type checkers, things that these other tools won't find. So CodeSpotter is one great way to get started. And let me go back here. So the other is we have the similar kind of offering that happens in the cloud, but this is free for all open source applications, and we call this Coverity Scan. This is it's really simple sign up process. So these are just some of the applications that are, or some of the open source projects that are currently using us. There's several thousand now that are C, C++, and Java applications that are using the service. A lot of Apache Foundation projects like Hadoop are using us. On the C, C++ side, like the Linux kernel foundation, the Linux kernel group themselves, do weekly analysis. And so by uploading an open source application here, or by being added as a contributor or as an observer to one of these applications, is also a really great way that you can see the analysis in action and get feedback. So that's all I'd like to say. I've got a few minutes left, but I want to just leave it open for any questions that people might have at the end. So thank you everyone for showing up. I hope you learned something. Thanks. Question? Yeah, I'll repeat your question, but just speak loud.
Yeah, okay. Can you write your hints? For instance, if you know that there's a certain prediction that has a problem in your own source code,
Okay. So correct me if I'm wrong, but you were asking if there's something that you'd like to check for that we don't do out of the box, and you wanted to customize or add your own. Yeah, that's certainly possible. There's different ways to customize. One of the basic ways is through modeling of different methods. So I talked about doing data flow analysis, and if there's third-party jars that we don't have the source code for, we can still do analysis that goes through these third-party libraries, but we won't necessarily be able to report defects that are in the third-party libraries themselves. And in some cases, it might be beneficial, for example, to add modeling to the code to help us better understand some third-party constructs or parts that we don't get right. And so that's a really powerful way to augment our analysis to help us, so that we'll actually find things. But if there's other classes of things that we don't check for, there's other ways you can extend our tool and find as well. And so I'm talking a little about from the Coverity perspective. Other tools have different types of customization techniques. Like Fortify, I know, has like a query language that you can use, or Checkmarks has a query language. Fortify, they have ways of writing you can write custom data sources and data syncs. So most tools do have some sort of customizability in that regard, yeah. Any other questions? It's hard to see with the lights, so. Okay. Well, let's wrap it up then. If you would like to come up and chat afterwards, I'll stick around for a few minutes. Thank you.